Hello everyone. In today's video, we are going to be looking at chapter 17.3, which is on area between a curve and a line. So the objective of today's lesson is to find the area of a region between a curve and a line. To find the area between a curve and a line, there are generally two cases that we could be looking at. First, we have the one on the left, which let's call it case number 1, and case number 2, which is what we have on the right. Let me first talk about the case number 1. In case number 1, we have the curve over here and then the line. The curve is represented by the equation y equals to fx, while the equation of the line is represented by y equals to gx. We want to find out what is this area bounded by the curve and the line, okay, which is this area A. So in order to do that, we first understand that the area under the curve, let's say from this point, okay, under the curve of this part up to this point where B is, okay, the area under the curve towards the x-axis is actually this area that I am shading, right? Okay, then if we were to look at the area under the line, okay, towards the x-axis, it would be considered this part. So what we can see is that to find out the area A, we will take the area under the curve, which is being represented by this definite integral, minus away the area under the line, which is being represented by this definite integral. Okay, and this will help us to find out the area of the shaded region. So with this idea in mind, let's move on to look at case number 2. In case number 2, we have this equation of the curve y equals to fx, as well as the equation of the line y equals to gx. We want to find out what is the area of the region A. So the area under the curve is this part from A to B, will actually be this part that I'm shading here. Okay, while the area under the line towards the x-axis is actually this part that I'm shading here. So this tells us that to find out the area A, we will be taking the area under the line, which is represented by this definite integral, minus away the area under the curve, which is represented by this definite integral. So in summary, to find out the area between a curve and a line, we need to be very clear about what exactly is the area under the curve and the area under the line, and then we do the necessary subtraction or sometimes maybe addition to find out the area that we want, right? Okay, in this diagram, you also notice that there is this part over here whereby it conveniently says that the definite integral from a to b of fx minus away the definite integral of gx for a to b could be combined into a single definite integral. How we manage to get this is based on our understanding of subtraction law for our integrals. Okay, so we see that the boundaries of the integrals are actually the same, so that's why we can actually combine it together. So similarly, for case number 2, we can also have a single integral to represent what we want. However, usually in my work, I will be focusing more on doing this kind of working rather than trying to figure out a single definite integral, because it is more intuitive that way, okay, to know what are the things that we are subtracting or adding, and also we can be more mindful about our boundaries, because it is not all the time that the boundaries will always be the same. Let me next bring you through some examples. We will first take a look at try 13, which is found in your textbook page 134. In this question, it has a diagram showing part of the curve y equals to 8x minus x squared. The line y equals to 7 cuts the curve at the points P and Q. We want to find out what is the area of the region over here. So just as I explained earlier on, we can think of it as subtraction of two pieces of things. So what we will see is that we can consider this segment here, which is the area under the curve, minus away the area under the line, which is this part here. Okay, so let me show you the working that I have. The first thing that we need to do is to know what is the value of the boundaries, because the question did not give us that. Since we know that the line y equals to 7 and the curve y equals to 8x minus x squared, they intersect at the points P and Q, the x coordinates of P and Q give us the boundaries that we want. So what we will do is to do simultaneous equation solving, which we have over here in the very first column. And then we do our substitution method and solve the x is equals to 1 or x equals to 7. So now I have deduced that x is equals to 1 over here and x is equals to 7 over here. Okay, then now we apply our concept that we developed earlier. The area of the shaded region will be the area under the curve, which is this part, minus away the area under the line, which I have written in purple already. Okay, so under the curve, minus away under the line. Alright, and then you would be able to solve your usual definite integrals and have the answer to be 36 units squared. Now, is there an alternative to solving this part here of finding the area under the line? I hope you have an answer, because this line y equals to 7, okay, forms a rectangle with the boundaries x equals to 1 and x equals to 7 as well as the x-axis. So this is none other than just a rectangle. So an alternative way to do this would have to be seen as having length times breadth. So the length here is 6 units and the breadth over here, okay, or maybe the other way around, I didn't check on it earlier, so this would be 7 units. Okay, so length times breadth, 6 times 7, we will get 42 units square for the area under the straight line, which is true because 49 minus 7 does give us 42. So this is an alternative that you might be able to see. But do take note that it is not all the time that we are seeing quadrilateral kind of shapes, or rather rectangle shapes like this. There could be times whereby it is trapezium or even a parallelogram, or maybe even a triangle sometimes. Okay, so in the event that maybe you really forgot these formulas, okay, so you can then apply this definite integrals, which is a very generic method. Next, we move on to try 14. So in this question, we want to find the area of the region. Oops, let me get my pen out. Okay, so we want to find the area of this region here. So the strategy that we will choose to have is that we find out the area of the bigger part, which is the area under the straight line here, and we minus away the area under the curve, which is this part. Let me get a different color, this part here. Do take note that although it seems as though the blue parts are in two different segments, it is okay to just consider from, let's say, A to B, to see these two parts as the definite integral from A to B of x squared with respect to x. You don't really have to segment it out to become A to 0 and then 0 to B. So this process is not necessary, all right? Because after all, it can be continuous. A to 0 and 0 to B, it does give us A to B itself. All right, so let's proceed in the solving. So likewise, we do not have the boundary values for our definite integral. So we need to know what is the value here and here. So we do our simultaneous equation and we find that this value here will be -2 and this value here will be 1. So we can figure out area of the bigger trapezium, which is this segment here. That will be the area under the straight line. So that is what we have as the integral here from -2 to 1, 2 minus x and dx. And then minus away the area under the curve, which is the definite integral of x squared from -2 to 1 with respect to x. Okay, then we will be able to solve to get the answer of 4.5 units square. Another way to go about seeing the area under the straight line, which is this part here, okay, is that what we can do, oops, let me correct this a bit. Okay, another way to see this part is that this shape is actually just a trapezium shape. So what you could do is half times sum of parallel lines. So let me just write it out here. So area of trapezium which is half times sum of parallel lines times its perpendicular height. So the sum of parallel lines would refer to this length and this length. However, we do not know the y values here. It is not difficult to find out what are these two values. We could easily take -2 to substitute it into the curve, or maybe even to the line, that's also fine, and take x equals to 1 and substitute into either one of the equation. So there's this extra step involved in finding out the sum of parallel lines. And then to find out what is the height here, you will be able to take the difference in number of units, so that will be 3 units. Okay, so I'll leave it to you to explore the option of finding the area of this trapezium by the conventional formula that we have used. Okay, to check that it is 7.5 units square as well. It should definitely get you the same answer. We will now take a look at try 15 that's found in your textbook page 134, where we want to find the area of this shaded region. The strategy that we will be employing over here to find the area would be to look at the area under the curve. Okay, from this segment, from this point here, up to this intersection point only. Alright, so we will be looking at this part, minus away this other part, which is a triangle actually. And that is the area under the straight line, y equals to -x minus 3. Okay, so that's the strategy that we will be using. And do take note that the areas that we are calculating, okay, of the one that's under the curve and under the line, these are all under the x-axis. So because it's all under the x-axis, do remember that we have to apply the negative to the definite integral. So let's proceed with the answer. So similar to before, we will do our simultaneous equation and then see that we have x equals to -3 and x equals to 2. So that tells us that it will be a -3 over here and a -2 over here. So the strategy that we employed earlier, or we figured out earlier, was to find the area under the curve. This negative is due to below x-axis. So this is area under curve. Minus away the area under the line. And this negative sign here is due to below x-axis. Okay, so while this minus is actually a subtraction of the bigger area and the smaller area. Okay, then we will do our usual solving. All right, there are many ways to go about handling this algebraically. So what I did is to take this subtraction sign and this one that is due to below x-axis to give me a plus over here. You could definitely factorize out the minus signs here, but I did not do that in my working. All right, you could go and try out the different algebraic methods and find a way that is comfortable for you, okay, and something that could give you the correct answer. So at the end, my answer will be 20 and 5 over 6 units square. Do take note that it is different from the one that's printed in your textbook. That's because the answer printed in your textbook is incorrect. Let's take a look at try 16 now, where we are shown a diagram. Part of the curve y equals to x squared minus 1 meets the x-axis at Q. The tangent at P meets the x-axis at R. And given that the x-coordinate of the point P is actually 3, we want to first find out the equation of the tangent, then proceed to find out the coordinates of R, and lastly to find out the area of the shaded region PQR. So in order to find out the equation of the tangent, we will need the gradient of the straight line, as well as at least the coordinates of one point that's found on this straight line itself. Okay, so with that in mind, let me show you the solution for part I. So I've written out the conditions that we need for part I over here, which is the gradient and coordinates of one point. Okay, so let's look at finding the gradient first. To find the gradient, naturally we will think of applying the formula, okay, which is the rise over run formula. But in order to do that, I need more information from this straight line, whereby I need the coordinates of 2 points. Okay, in this case, I do not have the complete coordinates of point P, neither do I have the coordinates for point R. So an alternative that we can do is that since this green line is a tangent, we have learned how to find the gradients of the tangent by doing differentiation. So y equals to x squared minus 1 is the equation of the curve, and by doing our differentiation, we will have 2x. So since we know the x coordinates of P, when x is equals to 3, we can substitute it into our dy over dx and figure out the gradient of the tangent to be 6. Then I can find out also what is the y coordinate of the point P by substituting x equals to 3 into the equation of the curve. And I will be getting y equals to 8. So the coordinates of P is now 3, 8. Then to find the equation of the tangent, we have the gradient over here, and we can also find out the full equation by using the coordinates of P. Okay, and then we will solve and find that the equation of the tangent will be y equals to 6x minus 10. Moving on to part 2, which is to find the coordinates of R. That means y is equals to 0. So we substitute in y equals to 0 into the equation of the tangent because R is on the tangent. And then we solve that x is equals to 1 and 2/3. Therefore, the coordinates of R will be 1 and 2/3, 0. Lastly, let's take a look at part 3, which is to find out this area. So let's develop a strategy to find out what is this area. This area can be seen as taking the area under the curve, which I am highlighting with these purple lines here. Okay, area under the curve minus away the area under the straight line, which is actually a triangle as well. Okay, and then I will be able to get the area of the shaded region that I want. So let's take a look at the solution. Okay, so I definitely need to know what is the x coordinate of the point Q in order to set my boundaries needed for my definite integral. So point Q is found on the x-axis, that means when y is equals to 0, I substitute it into my curve equation, and I will find that x is equals to 1 or negative 1 when I take square root. Due to the diagram that we are shown with, okay, Q is definitely found in the positive x-axis. So therefore, the x-coordinate of Q will have to be positive in value itself, and that is the reason why we reject negative 1. So Q is actually 1, 0. Okay, so the x-coordinate of Q is 1. Now, since we have developed our strategy earlier already, we will be taking the area under the curve, which is again what I am trying to emphasize with these red lines that I've drawn. Okay, so area under the curve is this part. Minus away the area of the triangle, which I have already shaded and represented it in green. An alternative way for this area under the line, okay, which is the area of triangle, I can do half times base times height. So my base could be considered as this, which is 3 minus 1 and 2 over 3 in length, and then my height would be here. But again, to find out the height, I will need to know what is the y coordinate of P, and that takes me some extra step. Okay, so 3 minus 1 and 2 over 3 times a height. That I will leave it to you to go and figure out. I hope that at this stage you will understand that trying to find the definite integral under a straight line may sometimes be easier, okay, and less troublesome than to find out the area of a triangle or trapezium, or sometimes even a rectangle or a square. Okay, so I hope that you appreciate this method, and then we can continue to solve, and our answer will be 1 2/3 unit square. Next, I want us to take a look at exercise 17.3, question 1c, where we want to find the coordinates of the points P and Q found in the diagram, and also to calculate the area of this shaded region. I'm going through this question because this is with reference to the y-axis instead of with reference to the x-axis. Okay, so let's bring back that concept that we learned in the previous lesson. So to find out what is the area, our strategy behind it is to find out the area of this rectangle actually, which is actually also the area of the line x equals to 2 to the y-axis. And then we minus away area under the curve, okay, which I have already highlighted in blue. I've already shaded it in blue, right? Area under the curve towards the y-axis as well. Okay, so what we need to first find, as per directed by the question as well, is to know what are the coordinates of P and Q, so that I know what are these boundary values over here that is needed for my definite integral. Okay, so I will do my usual simultaneous equation solving, and then I will be able to find that y is equals to square root 2 plus 2 or negative square root 2 plus 2. I have decided to leave my values in exact over here so that my answer in finding out the area of the shaded region will be more accurate. Alright, usually we do get integer values rather than irrational values like this. Okay, so whenever I get irrational values, I will always do a double check of my working just to ensure that I didn't make any careless mistakes and before I proceed on to solve. So the coordinates of P will be 2 square root 2 plus 2, and the coordinates of Q will be 2 comma negative square root 2 plus 2. Okay, so now let us apply the strategy that we have already developed. So we said earlier that we will find out what is the area under the straight line towards the x-axis. So this is the part that I'm referring to, which is area. I'll just very loosely say that it is under, okay, because it's after a matter of perspective, area under the line, minus away the area under the curve, which is the parts that I've shaded in blue already. So this is the part that is area under the curve. Okay, so I do my usual definite integrals, and then I will start solving, and I will find that there's a bit of a few steps involved because of the irrational value involved. Okay, if the question asks for an exact value, then all these steps will be necessary. Otherwise, you could have just pressed your calculator and leave your answer as 3SF 3.77 units square. That's perfectly fine as well. We have come to our very last question for this unit. Okay, so we are looking at exercise 17.3, question 7, whereby the diagram shows part of the curve y equals to kx minus x squared, and it intersects the x-axis at the point P, and then also Q3H is a point on the curve. So we want to find out what is the value of k. All right, and then in part 2, we want to find the area enclosed by the curve and the line OQ. To find the value of k, what we will do is to understand that since P20 is on the curve, we can substitute in the value of x equals to 2 and y equals to 0 into the equation of the curve, and then we will be able to solve to find that k will be equals to 2. So that's how we find the value of k. Now the main challenge over here is to find out what is the area enclosed by the curve. So let's develop a strategy to solve this. Okay, so do keep in mind that whenever we say area under the curve, it is bounded by the x-axis. So the area under the curve here only stops at this part. Okay, so if I were to do a definite integral from 0 to 2 for the curve function 2x minus x squared dx, it is only representative of this part that I have just shaded. Okay, then what happens to this remaining part? Okay, how do we go about determining this area? All right, so what we can do is to look at area under the x-axis. Okay, so the area under the x-axis, let me choose a different color. Okay, it is actually figured by, or rather bounded by, this part here. Let me draw it better. Okay, which is actually a triangle. So we're looking at area under, all right, I'm just loosely using it, area under the line towards the x-axis. Okay, so this part here is area under line, but take note that it is below x-axis. But since we only want to find the shaded region, we need to minus away the area of this shaded region, which is the area under the curve. Oops. Which is again below the x-axis as well. So all of these are below x-axis. So do be very mindful about that, because when it's below the x-axis, the negative sign is very important. Okay, so now that we have developed the strategy behind it, let's go about finding the values that we might need. So I have already placed our strategy at the top of this slide, which is that we will have to find the area of the blue part plus the area of the green part, which is actually this triangle that I have bounded it out by, minus away the area of the purple part that I've shaded. I'm not sure whether you see this as purple as well, but it is purple on my screen. Okay, do take note that this green and this purple part, they are actually below the x-axis. So we need to have the negative sign. Okay, so earlier on, we have already found that this blue part could be represented by the definite integral 0 to 2 for 2x minus x squared. That is the equation of the curve, since I've already found out the value of k, okay, which is equals to 2. And then the challenge here is to find out the area of the green part and the area of the purple part. Now to find the area of the green part, you may want to consider half times base times height, which is the area of the triangle. Okay, so P20, do be mindful that it is referring to this part here. P is this part that I've marked out. Okay, so if I want to use half times base times height, I will definitely need to know what is this value here, such that I can find out this base. And then also I need to know what is this height, which is the y coordinate of Q. So this is one way. Okay, another way which I am actually going to be doing as part of my solution that I have already written out here is that, let me just erase things out a bit. Okay, so this cross refers to the point P. Okay, so what I will need is the equation of this straight line in order for me to do a definite integral from 0 all the way to this point. Okay, and then I can find out the area of the green segment or the green triangle. Okay, so how do I go about finding the equation of this straight line? All right, I will need gradient. I will need to have one coordinate point as well. Okay, so but I don't really need one coordinate point, because after all this line intersects at the origin. So this means that the y equals to mx plus c, the c being the y-intercept, will have to be 0. Okay, so our aim now is to figure out what is this coordinate of Q, so that I can find the gradient of this straight line, because gradient I definitely need to have two coordinate points. So with y equals to 2x minus x squared, since Q is found on the curve itself, I can substitute in x equals to 3. That is the x coordinate of Q. And then I will be able to find out that the coordinates of Q will be 3, negative 3, and the gradient of OQ will be negative 1. So therefore, y equals to mx plus c, m is negative 1, and hence my equation of OQ is y equals to negative x. Okay, now let's piece everything up together. Okay, so the area of my blue part, which I have already told you just now, that is my definite integral from 0 to 2 of the curve dx. Keep in mind that the green and the purple, they are all below x-axis, so therefore I need to have this negative sign here. Okay, and I'm integrating the equation of the straight line from 0 to 3. Why is it 3? Because that is the x coordinate of Q. Okay, then I will need to minus away the equation of the curve, which is the purple part. Okay, equation of the curve, the purple part, from 2 to 3. All right, and do keep in mind it is below the x-axis again, so minus. Okay, so this minus here and this minus here is a result of below x-axis, while the plus sign here is due to our strategy, and this minus sign here is due to our strategy. Okay, so I go ahead to do my definite integrals, and then I can simplify and substitute in the values, and my final answer will be 4.5 units square. I hope that you're able to follow and appreciate this strategy. It's not very easy to conceptualize it, but with practice, definitely you can do it too.